So before we sum up some theorem here, I want to point something out. So we can use row operations to simplify a determinant, right? We can, use that to make things a bit easier. What we can also do, if you think about how determinants work, since we're allowed to expand upon rows and columns, we can actually do column operations as well. And the same rules apply. So if we flip two columns, it changes the sign of the determinant. If we take a column and we multiply it by some number, that changes the determinant in the same way. Right? If we combine two columns, then it doesn't change the determinant. So the exact same rules still apply for these column operations. Right? Now, again, I want to point out, it only works for determinants. You can't do column operations any other time. It only works for determinants because we can expand upon rows or columns. All right. So, using these ideas, let's point out a couple things real quick. So, look at this determinant here. Can you tell me the value of this determinant? Okay. So, if you think about it, since we have a row of all zeros here, if we do a cofactor expansion along the top row, everything's going to be 0. Okay? Let me sort of point out another thing here. What about 1, 2, 3, 1, 2, 3, 4, 5, 6, let's say. What if we have this? Well, what if, if we have this, we can do row 2 minus row 1 goes to row 2. All right, and this operation doesn't change the determinant. And that gives us all zeros here. So this determinant now has a row of all zeros. So that determinant's 0, right? For the same reason as above, we can just expand on that row. All right. What if we have 1, 2, 3, 4, 5, 6, 2, 4, 6? What if we have that? Well, if we look at this, the third column is just 2 times the first one. So if we do column 3 minus 2 column 1 goes to column 3, right? That column operation doesn't change the determinant. And we have 1, 2, 3, 4, 5, 6, 0, 0, 0. And now we have a column of all zeros. So if we expand upon that column, we get 0. So this gives us sort of 3 ways that a determinant can be 0, right? I mean, it all kind of amounts to a row of zeros. But here, if you have 2 identical rows or columns, right? Here, if you have 2 rows where one is a multiple of the other, or columns, again. And here, if you have a row or a column of all zeros, the determinant's going to be 0. So let's formalize that. Okay. Okay, so if A is an n by n matrix, n by n matrix, okay, then if any of the following is true, the determinant of A equals 0. All right? So these things are a row let me emphasize entire. So an entire row or column consists of zeros. Okay. Two rows, again, or columns are equal, or one row or column is a multiple of another row or column. All right? So these are convenient ways to look for whether a determinant is 0. Also, it's a convenient thing if you can sort of use row or column operations to create a row or column of all zeros, or to make two rows or columns equal to each other, or multiples of each other. If you can do that, then the determinant has to be 0. Now, of course, that only works if the determinant is 0 in the first place, but it's just a good thing to keep an eye out for as you're computing determinants. All right. So I hope that gives you a bit more insight into computing determinants and how we can kind of make things a bit easier. And in the next set of lectures, we'll start talking about properties of determinants and how sort of the elementary matrices come into play. So with that, I'll see you in the next one.